All right, welcome back. We are in section 3.2, talking about the second derivative and the behavior of functions. So we've already looked at how the first derivative can affect what a curve looks like, how a function behaves. We talked about the idea of increasing or decreasing. Now we're going to see how the second derivative plays a role in all of this. So first we need to recall what we've talked about previously, about how the second derivative of a function tells us about its concavity. And concavity indicates how a graph bends. So when we talk about a graph having concavity, we're not talking about whether the graph is going up or going down, but whether it is bending up or bending down. So consider a continuous twice differentiable function, f of x, defined on the interval from a to b. F double prime is positive for every x in the interval ab, if and only if f is concave up on that interval. So if we have a positive second derivative for every x on that interval, then we have a graph that is concave up. If on the flip side of this, we have a second derivative that is negative for every x on the interval, then that means that f is concave down on AB. So we have a few different examples of the types of graphs that we can see. So something like this. This one is, of course, concave up, right? You can see the upward bend to it. This graph here is concave down. So notice both of these curves are increasing, right? They're both going up from left to right, but this one is going up faster, right? This one is increasing at an increasing rate. This one, it's going up, but it's going up slower, right? It's increasing less and less every time we move over. So that's what's making it concave down, even though the function itself is increasing, okay? Same thing over here. This graph, even though it is decreasing, the bend is getting less and less negative, right? It's starting to level back out, and eventually we can imagine this going back up again. This one has an upward bend, so this is concave up, and this one decreasing and downward bending, so that's concave down. Okay, so a concave up graph typically looks like that. It's like a letter U for up. Concave down goes the other way. Now on a graph, points where there is a change of concavity. So we go from concave like up to down or from down to up. These points are called inflection points. And we can find inflection points using a similar technique to what we saw with the first derivative test in our previous section. So we take values where the second derivative, f double prime, is equal to 0 or undefined. And these are called not critical values like we saw in the last section. They're actually called hypercritical values. These hypercritical values give us possible locations of inflection points. So we take the second derivative, set it equal to 0, and then determine any possible locations of inflection points. What we would then do is check the concavity on both sides of that value to confirm if they are inflection points or not. So let's take a look at an example here. An efficiency study conducted on the day shift of a manufacturer showed that the number of units of a product produced by a typical employee T hours after 8 a.m. can be modeled by the function f of t is negative t cubed plus 9t squared, with t going from 0 to 8. So that's the 8 hours of their workday. In the context of this problem, describe the behavior of this function. Okay, so this function is telling us the number of units produced by an employee, right? So the higher the number that we get from this, the higher their productivity level is. We're going to look at some rates of change here. We're going to look at some derivatives. So we're going to take f prime of t, so that's negative 3t squared plus 18t. We're going to set that equal to 0. And solve this. So we can pull out, I'll pull out the negative also. A negative 3t. That leaves us with a t minus 6. So we get t equals 0 or t equals 6. These represent potential max or min values, right? These are critical values. That's what we found last time. But what I also want to look at is the second derivative. And we take the second derivative, we get negative 6t plus 18. We're going to do the same kind of thing. We're going to set it equal to 0. Let's see, factor out. Actually, I can just divide away. No, we'll just add that over. So we get 6t equals 18. So t equals 3. Excuse me. This is a hypercritical value. Okay, so we have two critical values over here, two possible locations of a max or a min, and we have one hypercritical value here that is a possible location of an inflection point. So let's go ahead and set up a number line. And we're going to put all these values on it. So 0, 3, and 6. So let's see here. Try to color code this. 0 is the beginning of the day, so we don't need to put anything over here. I'm just going to label this one. F prime will be on top, and then I'll do F double prime down below here. So we're going to check some values. So between 0 and 6, if we pick any value in between those two, take like 1, for example, we get a negative times a negative. That's a positive. And I know it's a little weird that this interval got split like this, but it is positive that whole way. And then beyond 6, so that would be from 6 to 8, right? If we plug in like 7, for example, that's a positive and a negative. So now we are decreasing right there. And then if we look at F double prime, we're going around 3 here. So from 0 to 3, so we'll pick like 1 again, for example. That's going to be a positive number. Okay, so that's concave up. So that's going to be something like that. Pick something beyond 3, so like 4, for example. That gives us negative 24 plus 18 is negative 6, so that's concave down. And it was all beyond just 3. 3 was our only hypercritical value, so that'll be concave down also. So now this is going to give us a picture of what exactly is happening here. So the function tells us how many units are being produced. The first derivative is the rate of change of that. So it's how much their productivity is as they go, right? How efficient are they, right? Because that's what this question is asking about, efficiency. So the rate at which they make those products is determined by the derivative. That rate is going up and up until we hit 6 hours, and then it's going down. And then the second derivative is giving the rate of change of that productivity level. Okay, so this one is increasing and it's concave up, so it's increasing at an increasing rate. So not only is their productivity and their efficiency going up, but it's going up faster and faster and faster. By the time we hit the 3rd hour, so that would be, 11 a.m., we are still have an increase in production, but it's starting to bend down a little bit. So they're still increasing the amount produced, but not as much or not as quickly. And then by the time we hit the 6th hour, which that's going to be, would that be 2 p.m., then now their productivity is not only going down, but it's bending down also. So it is decreasing, and it's decreasing faster and faster. So the way that we can describe this, trying to get this to, all right, there we go. So that first piece from 0 to 3, this is from 8 a.m. to 11 a.m. Efficiency is increasing. That's the first derivative. So let me color code this. Efficiency is increasing, and it's doing so at an increasing rate as well. That's what the second derivative tells us. Then on the second interval here from 11 to 2, efficiency is still increasing, but it's not increasing as quickly as it was. Okay, so efficiency still increasing, but at a decreasing rate. And then after 2 p.m., so from 2 p.m. until I think 4 is when their shift would end. Now efficiency is decreasing, and it's decreasing at an increasing rate. Now, notice increasing rate and decreasing rate, it's all relative here. So because this one is going up and bending up, it's increasing at an increasing rate. Because this one is going up but bending down, they're working against each other, it's increasing at a decreasing rate. So these are opposites. But with this one, it's decreasing at a decreasing rate. It's decreasing and it's bending down. So it's decreasing faster and faster and faster as it goes down. So that means that we are decreasing at an increasing rate. Or in other words, we are decreasing more quickly as time goes on. Okay, so that productivity level is dropping, as you can imagine it might at the end of a long day on a full 8-hour shift. Right, your productivity is going to get higher as the day progresses, right? You start waking up, that coffee's kicking in. Then maybe you go on like your lunch break and you're still increasing your efficiency, but you're starting to slow down a little bit. You're not increasing it quite as quickly. And then by the time you hit like afternoon break or something, last couple hours, you're ready to go home. And so you start losing that efficiency rate there. Okay? But these are the things that the first and second derivatives can tell us. So let's take a look at a few more examples. So first up, describe the behavior of this function. F of x is x to the 3/5 power minus 1. So let's take a look at our derivatives. So f prime of x, we're going to use the power rule. So we bring down the 3/5 and subtract 1. So that's negative 2/5. So that's the same thing as 3 over 5x to the 2/5. And the negative 1, the derivative of that is nothing. Let's see. And then f double prime of this. We're going to take the derivative again. So we bring down the negative 2/5. That's negative 6 over 25. And subtract another 1. That's negative 7 over 5. So we get negative 6 over 25x to the 7 over 5. In our search for critical values or hypercritical values, we would try to see where these functions are equal to 0, but there's no way that either of these would be equal to 0, because if you multiplied this across, it would turn into a 0, and then you would have 3 equals 0, which is not true. So these can never be equal to 0, but they can be undefined. And they're undefined when the denominator is equal to 0. So this is undefined when x equals 0, and undefined when x equals 0, so both of them. So now we're going to check and see what happens here at 0. So I'll put f prime up here, f double prime down here. So when we pick a negative value to put into f prime, so like a negative value right here, it gets squared, so it becomes positive, and then everything else that applies to it doesn't change that. So that's positive. And if I plug a positive number into here, it stays positive. So we are increasing and increasing like that. So what this means is there is no max or min for this function, because we're going up and then stopping and then going up some more. Okay, or not quite like that, because that would be a horizontal tangent, but we have an undefined value in between. We'll take a look in just a second. For f double prime, if we take a value less than 0, so a negative, it gets raised to the 7th power, which will still be negative. And then we take the 5th root of that, which will still be negative. So this will be a negative times this negative right here. So that's going to be a negative, so that's concave down, like that. Oh, sorry, I said that backwards, didn't I? Yeah, negative times a negative is a positive. So that's concave up. There we go. Because now on the flip side, if we put a positive in here, then everything is positive, and then there's the negative in the front. So this one's going to be the concave down right there. So at the value x equals 0, we go from concave up to concave down. So it does change concavity at that point. So there is an inflection point. So we abbreviate that IP at, let's see, when x is 0, y is -1. So at the point 0, -1. So this gives us a couple useful pieces of information. If we were to look at the function itself, so it's increasing into 0 and it's increasing out of 0. It runs through the point 0, -1. That's going to be down here. And it's going to be concave up and then concave down. So if I put that point on right there, change my color. And it's not going to be a horizontal tangent, because that would be if it was concave down and then up. That's not, it's the opposite. So it's concave up. So something like this. We have that undefined derivative here. That's because the tangent is vertical. And then it's still increasing, but now it's concave down. All right, so increasing, increasing, concave up, concave down, goes through the point 0, -1. That hits all of those conditions that we saw in our work. So combination of the first and second derivatives together can give us useful information when working with functions, and it can help us understand and visualize functions better than just maybe plotting points. For this next one, summarize the behavior of f of x here and sketch its graph. Okay, so we're going to do same kind of thing. So we're going to take the derivatives. So we get 3x squared minus 6x. We set that equal to 0. Factor. And we get x is 0 or x is 2. And those are the critical values. And for the second derivative, we get 6x minus 6. Set that equal to 0. So 6x equals 6. So x equals 1. And that's our hypercritical value. So now we go ahead and set up our number line. So we're going to have, let's see, 0, 1, and 2. And we'll do f prime first. So pick a value less than 0. That's going to be a negative and a negative, which is a positive. Between 0 and 1, take like 1/2. That's positive 3/2 and negative 3/2. So that's a negative. Between 1 and 2, let's see. Well, this is the same interval, right? For these two, it's just between 0 and 2. So it's the same thing. And then greater than 2, we get a positive and a positive. So we're going increasing, decreasing, increasing. And then for our second derivative, our concavity, value less than 0, negative minus a negative, so that's going to be negative, so concave down. And actually, we're only looking around 1 for this one, so this one will also be concave down. So we just have kind of a big concave down section. For a value greater than 1, you could even pick 2 if you want. You get 12 minus 6 is positive, so these are concave up, like that. So we do have some notable points here. We have a maximum occurring here, right? A relative maximum. We have a relative minimum occurring here. And we have an inflection point occurring here. Right, those don't really match up, but it's here at 1 because we go from concave down to concave up at that point. So we're going to have a relative max at 0, 4. we're going to have a relative min here at 2. So that's 8 minus 12 plus 4 is 0. So that's 2, 0. And we're going to have an inflection point at 1. And then let's see, that's 1 minus 3, negative 2 plus 4 is 2. So 1 comma 2 is an inflection point. So these are all of our notable points of interest. So now if we go to look at the graph, so because it asked us to sketch it. So let's see here. 1, 2, 3, 4. Just get a little bit of scale on here. Not going to be a perfect scale, but that's okay. Let's see. So we've got our max at 0, 4 up here. We've got our min at 2, 0 down here. And our inflection point at 1, 2 right there. Okay, so everything from 1 to the left is concave down. So like that. Everything to the right of 1 is concave up. So something like that. Okay, so it's good sometimes just to rough sketch it out first, so you know where everything is supposed to go. So there's our concave down. And now it flips to concave up. It hits our min. And it does something like that. So we have increasing, decreasing, increasing, concave down, concave up. So that matches all of our different conditions there. So now the last thing we're going to talk about in this section, we're going to, oh nope, before we get to the last thing we're going to do one more example. So, because this one's kind of interesting. So we want to summarize the behavior of this function. We have 5x plus 2 over 3x minus 4. If we take the derivatives of these, the first derivative does involve the quotient rule. I'll just tell you what we get. We get negative 26 over 3x minus 4 quantity squared. And the second derivative gives us, this one, you don't even have to use the quotient rule. You can just use the chain rule and the power rule. It would give us positive 156 over 3x minus 4 quantity cubed. This one will be undefined when the denominator is 0, so that's when x equals 3/4. Nope, sorry, 4/3. I wrote that backwards. 4/3. And then same thing with this one. This is undefined when x is 4/3. So that's our critical value. That's our hypercritical value. But if we set this up on a number line here, and we check a value to the left, so I'll do first derivative. Check a value like 0, we get 2 over negative 4, so that's negative. Check about a value bigger than 4/3, so like 2, that's 12 over, 12 over 2, spaced out there for a second. 12 over 2, so that's going to be a positive. Wait, did I mix that up? Oh, I'm being silly because there's a negative right here. I'm looking at the wrong one. Sorry. Yeah, actually, this one will always be negative, right? Because this term gets squared, and then this term has a negative in front of it, so that'll be negative and that'll be negative. So we're just decreasing the whole way. And then for the second derivative, this one could potentially change. If we pick a value like 0, we get a negative down here. That cubed is still negative, so negative, so that's concave down. And if we pick a value like 2, that's a positive, so we get concave up. So it stands to reason just from this analysis here that there are no relative extrema, right? No maxes or mins, because the graph starts up that way and it just keeps going down that way. It does appear that there would be an inflection point at 4/3 because it goes from concave down to up. However, this function is rather unique. If you try to find where that point is to get that inflection point, we're not going to be able to do it because if you plug in 4/3 into the function, you end up getting a denominator of 0. So it turns out that f of x does not exist at x equals 4/3. So there are no relative extrema. We already knew that. But this one value that could have been an inflection point is also not an inflection point because there's no point there, right? It's actually going to be an asymptote, a vertical asymptote. So no relative extrema and no inflection points. So it turns out that the graph of this function, there is a vertical asymptote here at x equals 4/3. And this isn't necessarily something we need to talk about right here, but we can use other concepts like the idea of limits to determine the long run behavior of it. So actually, if I move this over slightly, so note, if we took the limit as x approached positive or negative infinity of 5x plus 2 over 3x minus 4, that limit is 5/3. So somewhere up here, there is a horizontal asymptote at y equals 5/3. So our curve is actually going to look something like this. Maybe I'll make it a little bit smoother than that. Like that. And like that. So this is the reason that we get those weird values that we do. So notice it's decreasing. And then even though the function has this weird jump up to here, it never turns and goes up there. So it is still decreasing on both sides of this value. And it does change concavity. It goes from down to up, but there is no single point where this occurs. So there technically is no inflection point either for this curve. So kind of a unique one. I think it's good to see a less typical example at some point while we're working on this stuff. So now the final thing that we need to talk about in this section is kind of just formalizing what we were just talking about with these second derivatives. And that is the second derivative test. So we talked about the first derivative test in the last section. Now we have another way of determining relative maxes or mins using second derivatives instead. Second derivative test says, if a function is such that f prime and f double prime exist and the number c is a critical value of f, then if f double prime of c is greater than 0, so if the second derivative at the critical value is positive, f has a relative minimum at x equals c. If the second derivative at the critical value is negative, f has a relative maximum at c. And then we have our third kind of tag-along case here. If f double prime is equal to 0, then the second derivative test is inconclusive. That basically means that that point is also an inflection point, and it doesn't give us any useful information. So we would have to go back to using the first derivative test if that was the case, which we absolutely can do. But for this one, I want to talk about these two really quick, because this usually is a point of some confusion, because people see f double prime being positive. They think positive, they think large number, they think max, but it's actually the other way around. If f double prime, so if we know that c, our critical value, is concave up at this point, that means the graph is going to be like this. Right? This is concave up, and a critical value has the horizontal tangent down there. So the curve looks like this. The critical point is down here. It must be a minimum down here. Okay, so when you see this definition, it's good to just picture that graph, and the point is at the bottom. Same thing here. If we have a critical value and it's concave down at that value, looks something like this. Okay, our critical value, horizontal tangent right there. This is going to be a max because it's at the top of the curve. Okay, so we can use this to determine maxes and mins in cases where the second derivative is easier to calculate. So both of these tests do work. They're both like equivalent. Obviously, this one has the occasional case where you get an inconclusive result, but it can be a good help to us as well. So let's try an example out with this. Find all relative extrema of this function f of x. So we're going to get the critical values first. So we're going to take the derivative. So that's 3x squared plus 9x minus 12. Set that equal to 0. I'm going to divide the 3 away. Just make these numbers a little easier to work with. Let's see. So that would be probably plus 4 and minus 1, I believe. So we get x equals negative 4 and x equals 1 as our critical values. Now, instead of doing a number line, we're going to take the second derivative. So that's going to be 6x plus 9. And we're going to just plug in these critical values into the second derivative and see what we get. So that's negative 24 plus 9 So that's negative 15. That's less than 0. So that means that the graph at negative 4 is concave down. Right, looks like that, which means our point is at the top. So that's a max. F double prime of 1, we get 6 plus 9 is positive 15. So a positive number means concave up, which means our point is at the bottom. And that's a min. And now we don't need to do a number line at this point. So this kind of replaces that process. Like I said, this won't be easier for every function, but for functions like this, it is fairly straightforward to just work with 6x plus 9 instead. But we end up with, relative max at negative 4. If you were to plug that back in, I'll just tell you, you get negative 4 comma 67. So kind of work for a calculator there. And a relative min at 1 comma 9 halves is the value we would get there. Right, so we're able to get those values, and if you check it independently using the first derivative test, you'll see you get the same result. But now this is another tool, kind of in our toolkit, of different types of tests that we can use to find relative extrema for a function. But that brings us to the end of section 3.2. That's our introduction to second derivative and the second derivative rule, concavity and inflection points. When we come back in the second half of this chapter, we're going to be looking at some applications and using these derivative rules to be able to determine max and min values for modeling problems. So I will talk with you all in the next one.